Yesterday we introduced the idea in class of light being something other than a wave. Said yesterday with our little demonstration, our little analogy demonstration that we did, that light exists not only as a wave, but as a particle as well. That idea came from Einstein in 1905 to explain a concept or to explain an experiment that was first done by Heinrich Hertz in 1887, almost 20 years earlier, called the photoelectric effect. The photoelectric effect essentially says that when light strikes a metal, an electron is sometimes ejected. Hertz tried to explain it using classical wave theory, but it just didn't work. So Einstein in 1905 introduced this theory that we call photon theory. And this photon theory is kind of at the beginning of the quantum revolution, of quantum theory. Photon theory says basically that light, or EMR in general, exists. Yeah, it exists as a wave. We're not throwing that away, but it also exists at the same time as a particle. It's like it can't decide. It's like it doesn't know what it wants to be, a wave or a particle. It's a fence sitter. Hey, I'm a wave. No, I'm a particle. I'm a wave. No, I'm a particle. There's evidence to support the wave nature of EMR, and that's still valid. But there's also evidence that supports the particle nature of EMR, which is also valid. All right. A photon we will define as a, well, we think of it as a particle of light, a little chunk of light, but it's technically defined as a quantum of energy, a little bundle of energy, a package of energy. We can think of it as throwing rocks. If I go to the playground and pick up a handful of those tiny little pea rocks, those pea stones, and start throwing them, each of those would be a photon, a little bundle of energy, a little particle of rock, except that we're talking about a particle of light now. And a photon, you learned yesterday, has an energy that's related to the frequency. And that's really where Einstein's explanation came from, was the idea that energy of a photon was related to the frequency. That's why it worked. Hertz said that the energy is related to how much light you have. Einstein said, no, it's not. The energy is related to the type of light you have. In other words, the frequency of light that you have. If you have a higher frequency of EMR, then you've got a higher energy of EMR. Whereas, again, Hertz said that you take a flashlight, make it brighter, well, that's more energy. You take a flashlight, shine it upon the surface for longer, well, that's more energy. But that's not correct. Okay, Einstein said that's not what it is at all. Einstein said that it's the frequency or the type of EMR that results in having different amount of energy. So we say that energy, the energy of a photon, the energy of one particle or one of light or one quantum of energy, the energy of a photon measured in joules or electron volts, could be either one, although joules will be your go-to. If you're not sure which one you should use, always use joules. Sometimes electron volts is convenient. Sometimes it's really convenient. But joules always work. So if you're not sure, go with joules. F is the frequency of the EMR, the frequency of the photon. See, we're not doing away with the wave nature of EMR, right? Just because we're introducing the particle nature of EMR or the quantum nature of EMR, we're not doing away with the wave nature. Otherwise, we wouldn't be talking about frequency. Frequency is a wave property. But yet we're putting it into an equation that describes the energy of a particle of light. The frequency of that photon is measured in hertz, by the way. H is a constant called Planck's constant, named after a guy named Max Planck. He was one of the guys who was involved in the infancy and the whole beginning of quantum theory, Max Planck. And this is where photon theory kind of developed from, was this beginning of quantum theory. So he gets a constant named after him. The value of Planck's constant is 6.63 times 10 to the minus 34 joules seconds if we want our answer to be in joules, or it would be 4.14 times 10 to the negative 15 eV times s, electron volt seconds, if we want our answer to be in electron volts. Now, we know that frequency is equal to V over lambda, right? V is equal to F times lambda. So frequency F is equal to V over lambda. So what we often do is add another term onto this equation, not just E is equal to H times F, but rather E is equal to HC over lambda. C is the speed of light, 3.00 times 10 to the 8 meters per second. And of course, lambda is the wavelength of the EMR, or the wavelength of the photon, and that's going to be measured in meters. So prior to this, like, we were certain that EMR was a wave. And EMR exhibited all these wave properties that showed us that EMR is a wave. Now we're saying that EMR is also a particle, and it must be, otherwise it wouldn't correctly explain this photoelectric effect that we were talking about a little while ago, and that we'll talk about in more detail a little bit later on. If the energy of a little bundle of light wasn't equal to H times F, well, if we didn't have a little bundle of light or photons, then we wouldn't have an energy of a bundle. And if the energy of that bundle wasn't equal to H times F, okay, then this whole thing wouldn't work. Then we still wouldn't be able to describe why the photoelectric effect behaves as it does. Quick little example here now is to put into action what we just learned about photons and the energy of photons. Question says, determine the energy of a photon that has a frequency of 5.0 times 10 to the 14 hertz. This is an easy question. It's about as easy as it gets. The energy of a photon is equal to H times F. It's also equal to HC over lambda, but we're going to use the HF part of it since we have the frequency. The value of Planck's constant that we're going to use, we actually get to decide. Since the question doesn't specify whether we want an answer in joules or electron volts, we can decide whether we want our answer in joules or electron volts. I'm going to go with joules. If in doubt, go with joules. Therefore, I'm going to use the constant, 6.63 times 10 to the negative 34 joules seconds. If I wanted my answer in electron volts, then I'd probably go with the 4.14 value, the EV seconds value. Now my frequency is 5.0 times 10 to the 14 hertz. When I multiply those two numbers together, I'm going to get 3.315 times 10 to the negative 19 joules, or 3.3 times 10 to the negative 19 joules. There's my energy in joules. As I said, if you want it in electron volts, then use the 4.14 value for Planck's constant, or the alternative to that is to say 1 EV over 1.6 times 10 to the negative 19 joules equals XeV over 3.315 times 10 to the negative 19 joules. And then just solve for X. In this case, it would work out to be, I think it would be like 1.1, 1.2. Sorry, 2.1? 2.07, 2.1? Yeah, I meant 2.1, 2.2, not 1.1, 1.2. So 2.1 electron volts it would be. Joules is fine. Okay, I didn't specify whether it's joules or electron volts. I'm just saying that if it did specify and you needed to do it in electron volts, you could either use the 4.14 value for Planck's constant, or you could just solve it in joules, the go-to method, solve it in joules, because that always works, and then convert it to electron volts after that. All right, you got a worksheet on the photoelectric effect. It's worksheet number 20. I'd like you to take a look at the first two questions, please, on that worksheet, and only the first two questions right now. Let's take a look at another example now, a second one that's a little bit trickier, not bad, but a little bit trickier than what we did in the last one. It says, how many photons of frequency 1.0 times 10 to the 16 hertz would it take to obtain a total EMR energy of 2.5 times 10 to the 22 joules? Do you remember back in Unit 2, in our electricity unit, one of the questions you got was, how many electrons do you have? Do you remember how to do that? How many electrons do you have? How many of anything? What's the number of anything? We always take the total amount of something and divide it by the something for 1. So for electrons, it was the total charge divided by the charge of 1. This time it's going to be the total energy divided by the energy of 1. So we'll say the number of photons equals the total energy divided by the energy of one photon. Now we have the total energy here is 2.5 times 10 to the 22. I don't have the energy of one photon, but I know how to find that. Okay, that's what we just spent a little bit of time doing with that equation. E is equal to h times F. So we're going to use, since we have our total energy in joules, we definitely want to be in joules here. We'll use the 6.63 value times 10 to the minus 34 joule seconds. That's on our data sheet, by the way, if you forget it, times 1 times 10 to the 16 hertz. When I multiply those together, I'm going to end up with 6.63 times 10 to the minus 18 joules. And if I sub that in here as 6.63 times 10 to the minus 18 joules, then I end up with a number of photons equal to, let's see here, 2.5 times 10 to the 22 divided by 6.63 times 10 to the negative 18 gives me a whole lot of photons. 3.8 times 10 to the 39. Sorry, there is no number associated with that, right? It's just a number. How many fingers do you have on one hand? 5. So we don't say 5 meters. Okay, that would be big fingers. If you had 5 meter fingers, those would be big fingers. We don't say 5 kilograms because those would be heavy fingers. We just say 5. You could say photons, yeah. Just like if I said how many fingers do you have, you could say I have 5 fingers, right? But that's not really a unit. So it would be okay to say that many photons, or it's just okay just to say that's the number there. Seth, question? Same question? Okay. All right, what I'd like you to do now, please, is take a look at these 3 questions on page 707 of your book. The first 2 questions are real similar to the questions you've already done. This third question is similar to the example that we just did.